So we talked about the dienophile. There's also the diene. And so the simplest diene is our butadiene, butadiene. And of course, this central bond still has some single bond character, and so it's free to rotate. And so what we call this left side here is the S-cis state, whereas this other one is the S-trans state, right? Indicating that the double bonds are on the same side or on other sides. And so if we think about our cycloaddition reaction, this left one can undergo Diels-Alder. While the one on the right can't. And it can't do that right because if you think about the Diels-Alder, we need these pi bonds on the same side so that they can join together with the dienophile. And so the other problematic part is that the one on the right is actually the preferred conformer. Right, due to sterics. But it's not too big of a deal at room temperature or elevated temperatures that rapidly interconvert with one another. And so you can get the product, you'll get the S-cis at some point, which can undergo the Diels-Alder cycloaddition. It gets more problematic when you start adding kind of functional groups here, right? If you start adding really big functional groups, you would really slow down the rate of this reaction. The other issue is when these dienes are in cyclic compounds. So for example, if you had this diene, right, it's cyclic. And so you can see there's no way these can form the cis phase. They're locked into the trans. And so if you try to react this with a dienophile, you'll get no reaction, right? There's just no way it can go into the S-cis modality. Whereas if you take a diene that's locked into its S-cis phase, the most popular being cyclopentadiene, right? Now it's locked into S-cis. This will rapidly undergo any kind of Diels-Alder reaction. And it's actually so reactive that it'll undergo Diels-Alder reaction with itself, right? So it can act as both a diene and dienophile. And so if you're trying to buy this compound, you actually can't bottle it. You would buy the dimer, right? So after the Diels-Alder cycloaddition, and then you would just heat it up to a high temperature to get your cyclopentadiene back. Right, so it's so reactive, it will react with itself. And then, of course, we can add some kind of dienophile to have it react. And so think about what it's going to form here. It's going to form our cyclohexene. But then it's also going to have this bridge right here, which is going to look something like this. If you want to draw it like this, in this case, A and B are trans with one another. So one of them will be a wedge, one of them will be a dash, and this will be a very fast reaction. And so this is one way to draw this compound. The other way is the more three-dimensional type of way. And so we do is we draw a cyclohexane, but now because of this bridgehead, it's locked into this type of kind of puckered position. And then we have this double bond right here. And then in this case, we have A as a wedge. So A is pointing up and then B is pointing down, right? Where the other hydrogens, there's a hydrogen pointing down here. And then this hydrogen is pointing up as well. So we'll take a look at these bicyclic compounds more later on. But overall, right, what we want is this S-cis conformer because it's more reactive.